Okay guys, so let's go over how we're going to check out the different disturbances for acid-base balance. The first thing that we need to know is that when we are doing this, the first thing we have to determine if it's an acid, acidemia, or alkalemia. So I'm going to put A and B, for A for acidosis or acidemia, and B for alkalemia or alkalosis. And we determine this by determining the pH. The second thing that we need to determine if it's respiratory, if it's metabolic, or if it's mixed, which we'll explain in a second. Now, if it's respiratory, we do 3, which is basically determining if it's acute or non-compensated, or chronic or compensated. Okay? In the case if it's not respiratory, but it's a metabolic acidosis, and to MAC, we do another 3 because we wouldn't be doing we wouldn't do it if it's acute or chronic. We will determine if it's going to be with a normal or an increased anion gap. And that's it. Now, in metabolic disturbances, we can also calculate if the CO2 change is consistent with the pathology. So in metabolic acidosis we do this formula, and metabolic alkalosis we do this formula. But we don't need to do it for this class. Okay, so just so you know that can be done later on. Okay, so and we'll obviously also see what happens with the different parts of this Davenport graph. So let's say, for example, we start off here. And so the idea is, if we remember that pH should be 7.4, and less than that is an acidemia, more than that is an alkalemia. Bicarbonate should be 24. Less than that means an acid type problem. More than that means a base type problem or situation. And the partial pressure of CO2, we remember, is going to be 40. More than 40, that means I'm accumulating CO2 and accumulating acid, so it's an acid disturbance. Less than that, I'm eliminating CO2, then eliminating hydrogen, so that's going to be a base problem. So we can do like, if you want, you can do arrows and determine different things. So pH that is low means that there's going to be an acidemia. That's it. Bicarbonate, it's still in range because we know the range is between 22 and 28, but it's higher than 24. That doesn't make a lot of sense. How it can have acidemia or more base? So we check the CO2, and CO2 is high. And CO2 being high means an acidosis, a problem with acid. So I have an acidosis with high CO2. That's another way of saying I have acidosis caused by the respiratory system. And the increase in bicarbonate is a buffering mechanism. So that means there's an respiratory acidosis. I first determine acidosis by looking at the pH, and then by looking at CO2 and bicarbonate, determine it's a respiratory acidosis. Sorry, I don't have a tablet with me. So if it's a respiratory acidosis and it's respiratory, I need to determine if it's acute or chronic. Simply put, either if it's chronic or acute, the bicarbonate will increase. If it's acute, if I haven't had a chance to compensate, the increase is small. If it's chronic or compensated, I have left enough time for the kidney to reabsorb bicarbonate and form new bicarbonate and secrete hydrogen. So if the value is close to normal, it should be an acute respiratory acidosis. If it's farther away, it's going to be a chronic. So in this case, 28 is close to 24, and I assume it's an acute respiratory acidosis. And it is an acute respiratory acidosis. But to make sure, we can use this formula. We can say for every millimeter of mercury that I increase in CO2, if I increase 0.1 of bicarbonate, that's acute. If I increase 0.4, it's chronic. So what we do is, we say, well, how much did CO2 increase? So 60, which is the number I have, minus 40, which is the normal amount of CO2. That means that I have increased 20 millimeters of mercury CO2. And I multiply 20 times 0.1 and 0.5. So 20 times 0.1 is 2. 20 times 0.4 is 8. And I add those two numbers to 24, which is the normal bicarbonate level. So 24 plus 2 equals 26 plus or minus 8. So it could be 26, and we can increase it. We can say between 24 and 28 is an acute respiratory acidosis. And 8 times 24 is going to be 32 plus or minus 2. So again, between 30 and 34, that would mean that the respiratory acidosis is chronic. So in this case, like we said, because the bicarbonate is close to normal, that's going to be a respiratory acidosis, which is acute. And the other way to see this is what happens to my graph. And again, we start off here. We have to look for 7.4. We have 7.4 here. And then 7.4, we match it with 24, which is here. And that means this green line here represents the patient and normal. This is the patient which is normal. So now the patient, when they have the respiratory acidosis, like for example, if I have asthma or emphysema, at the beginning, the patient will just decrease their pH, so it has to go towards the left to make a lower pH, and changing the curve from a 40 curve to a 60 curve because I'm accumulating CO2. So reaching 1 is the patient, what we have with the patient. Now, if I give enough time to the patient, eventually the patient will reabsorb and form new bicarbonate. So bicarbonate will increase, and as bicarbonate is increasing, the pH will try to go back to normal. It never reaches fully 7.4, but it's close to it. So 2 would be a chronic or compensated respiratory acidosis. Let's use another example, guys. And this already says so, but we can check it out and I'm going to explain in a second. So a pH that is high, that's an alkalosis. I don't care what else, but it's an alkalosis. It could be mixed, it could be respiratory, it could be metabolic, but it's an alkalosis. And I have an alkalosis or a high pH with a high bicarbonate. That makes sense. High pH with more base. That makes sense. So we may think of a metabolic disturbance. When we look at CO2, CO2 is high. The patient is hyperventilating and have low CO2. And that also is a base. So high base with bicarbonate, high base with low CO2. That means the patient has two diseases. One is a respiratory alkalosis, one is a metabolic alkalosis. And this patient now has a mixed alkalosis. I don't have to do anything else with this patient, and with that I have a value. Now the one that's below that, pH is low. So acidosis, bicarbonate is high. That means a thing with the base. So it probably is going to be a respiratory acidosis, so we make sure by looking at CO2. CO2 is also high. So yeah, this is a respiratory acidosis. Now looking at this, we can see that CO2 does not increase that much, and bicarbonate is much higher than 24. So my idea would be this will be a chronic respiratory acidosis. Again, if I want to make sure, I subtract 50 from 40, and that's 10. And 10 multiplied by 0.1 is 1. 10 multiplied by 0.4 is 4. And I add that to 24. 24 plus 1 is 25. So between 23 and 27, that should be if it's acute. And 24 plus 4 is equal to 28. So 28, it will be 26 until 30 is going to be a chronic. So because it's a higher number, there's going to be chronic respiratory acidosis. And we already saw the graph. So the one that's below here, let's look at the other one. We can see that pH in this case is low, so it's an acidosis, but low bicarbonate. That makes sense. I have an acidosis with low base. So it's probably a metabolic disturbance. So we want to make sure by checking CO2. And if the patient has CO2 that's low, that means the patient is hyperventilating. So that means they're eliminating the excess CO2. And less CO2 or low CO2, we think of base. So this has to mean that it's probably a metabolic acidosis, and the patient is hyperventilating as a way to compensate. So we already determined it's an acidosis, it's metabolic. What we need to know now, because in metabolic acidosis, I need to determine what is the anion gap. And anion gap, remember, is the positive, which is sodium, minus the sum of the negative things, which is going to be, in this case, chloride and bicarbonate. And just by looking, I didn't have to do the calculation. I know that this patient has a high anion gap, because if sodium is 138, and we know that bicarbonate is 11 and chloride 90, that's 138 minus 101. That for sure is higher than 15. So this is a patient with metabolic acidosis with an increased anion gap. So it can't be a patient with diarrhea, it can be a patient with hypochloremia, it can be a patient with renal tubular acidosis. It has to be one of the causes that is with an increased anion gap, which can be diabetes mellitus, starving ketoacidosis, etc. And finally, I could do this. You need to do this. I can do Winter's formula to determine if the partial pressure CO2 is normal for this situation, which is multiplying, as you see here, 1.5 times bicarbonate, so that's going to be like 16 in this patient. 1.5 plus times 11 should be 16. This plus 8, which 16 plus 8 is going to be 24. So between 22 and 26, that should be the normal CO2 in this patient, which the patient is, so we have a normal compensation from the respiratory system. And here the formula, the graph will go first from the green dot. Here is normal. The patient is losing bicarbonate because they're gaining acid, so they go from there to 1. And then as the patient is hyperventilating, the CO2 will decrease, and this will take the pH back to normal. Okay. Now this one here, bicarbonate is low because pH is low, so it's an acidosis. Bicarbonate is low. We're thinking probably a metabolic acidosis. But when I see CO2, CO2 is high. That also means acid. So we have, in this case, very simply, a mixed acidosis. I don't have anything else to do. So the idea is, so we can end it here, is that you can check the other ones, and you can ask me in the next class both that and the part regarding the Davenport diagram. So we can use that part to review before we begin with the endocrine system. Thank you very much, guys. Have a lovely day and weekend. Bye.